On a clear day, the sky above us appears blue. This is such a familiar sight that it almost fades into the background of daily life. Children draw blue skies in pictures. Weather forecasts show blue skies to represent calm conditions. And when clouds clear after rain, the return of blue overhead often signals that the storm has passed. But something about that color is actually strange, because space itself is not blue. When astronauts look out from orbit, the background of space appears completely black. And sunlight, the source of all this daylight, does not appear blue either. Sunlight looks white. So how does white sunlight passing through invisible air turn the entire sky blue? What is really happening to sunlight as it travels through Earth's atmosphere? To answer that question, we first need to understand what sunlight actually is. Although sunlight looks white, it is really a mixture of many different colors combined together. If sunlight passes through a glass prism, it spreads out into a band of colors known as a spectrum. These colors range from red and orange through yellow and green and into blue and violet. Each of these colors corresponds to a different wavelength of light. A wavelength describes the distance between repeating peaks in a light wave. You can imagine light as a series of tiny waves moving through space. Some waves are long and stretched out. Others are shorter and more tightly spaced. Red light has relatively long wavelengths. Blue and violet light have much shorter wavelengths. This difference in wavelength turns out to be very important when sunlight passes through Earth's atmosphere. Now consider the journey sunlight takes before it reaches our eyes. Before sunlight arrives at the ground, it must pass through Earth's atmosphere. The atmosphere is made of countless tiny molecules, mostly nitrogen and oxygen, along with very small particles suspended in the air. Although these molecules are far too small to see, they interact with incoming sunlight. When light encounters these tiny molecules, something important happens. Instead of continuing straight ahead, some of the light is scattered. Scattering simply means that light changes direction and spreads out. Rather than traveling in a single straight beam from the sun to the ground, part of the light is redirected across the sky. This scattering process is the key to understanding the color of the sky. But not all colors scatter in the same way. And that difference leads directly to the blue sky we see above us. To understand what happens next, imagine the atmosphere as a vast field of tiny invisible scatterers. As sunlight enters this field, different colors of light interact with air molecules in slightly different ways. The crucial detail is wavelength. Air molecules interact differently with different wavelengths of light. Shorter wavelengths scatter much more strongly than longer wavelengths. This phenomenon is known as Rayleigh scattering. Rayleigh scattering describes how very small particles, much smaller than the wavelength of light, scatter shorter wavelengths far more efficiently. In everyday terms, this means blue and violet light scatter far more than red light. So when sunlight enters the atmosphere, blue wavelengths are redirected in many different directions by the air molecules. Some of this scattered light travels downward toward the ground. Some spreads sideways. Some travels upward. Because this scattered blue light arrives from all directions, the entire sky appears softly illuminated with blue light. Imagine shining a flashlight through a fine mist. Instead of seeing a narrow beam, the light spreads throughout the mist, making the air itself appear to glow. Earth's atmosphere behaves in a similar way. Sunlight enters as a beam from one direction. but the atmosphere redistributes part of that light across the sky. Because shorter wavelengths interact more strongly with air molecules, the redistributed light is dominated by blue. This is why the sky appears blue when we look away from the sun. Blue is not actually the most strongly scattered color. Violet light has an even shorter wavelength and scatters even more. But our eyes are much more sensitive to blue light than to violet. And some violet light is absorbed by the upper atmosphere. So the scattered light that reaches our eyes appears mostly blue. This phenomenon reveals something interesting about how we perceive the sky. When we look upward, we are not really seeing empty space. We are seeing sunlight that has been redirected by the atmosphere. The sky itself is acting like a giant, natural light diffuser. This also explains why the sky changes color during sunrise and sunset. When the sun is low on the horizon, sunlight must travel through a much thicker layer of atmosphere before reaching us. Along this longer path, most of the blue wavelengths scatter away before the light reaches our eyes. What remains are the longer wavelengths, reds and oranges, which scatter much less and continue traveling through the atmosphere. That is why sunsets often glow with warm colors. The blue light has already been scattered out of the direct sunlight. So what is really happening when the sky appears blue? The answer comes down to how sunlight interacts with the air around our planet. Sunlight arriving from the sun contains many different colors. As this light passes through Earth's atmosphere, tiny air molecules scatter shorter wavelengths much more strongly than longer ones. This process, called Rayleigh scattering, redirects blue light in all directions across the sky. Because this scattered blue light reaches our eyes from every part of the sky appears blue to us. When the sun sits lower on the horizon, sunlight travels through more atmosphere. Most of the blue light scatters away before reaching us, leaving behind the reds and oranges that color the evening sky. The sky is not truly blue on its own. It becomes blue because of the quiet interaction between sunlight and the invisible air surrounding our planet.